So in our reaction today, what we'll be doing is studying the reaction between iodide and persulfate. The reaction looks like this. So this is iodide and this is persulfate. Oh, sorry, S2O8. And that's going to make iodine plus sulfate ion. And our goal in studying this reaction is to determine the rate law for the reaction relative to iodide and persulfate. So the rate law, generically the rate law, would look something like this. I'll write it down here because I have more to write under that reaction. Rate is equal to K times the concentration of iodide to some power, so let's just call that X, times the concentration of persulfate, and we'll call that Y, like that. So our goal is to figure out what the values for X are, what the values for Y are, and then to figure out the value for K from a reaction rate that we calculate from our data. Okay, so that's our goal. So what does this reaction look like? Well, iodide and persulfate are colorless. So when you mix them together, you get a colorless solution. What happens, though, as the reaction proceeds, you produce iodine. Now, iodine in the non-aqueous crystalline form is this deep purple color. But when it's in an aqueous solution, and all these are aqueous, dissolved in water, it's a brown, sort of muddy-looking solution. It starts as a yellowish brown and then intensely gets darker and darker as the reaction proceeds. So what we want to be able to do, though, is to measure the rate of the reaction, and we're going to be doing it based on iodine. So if you remember what that would look like in an equation, right? Rate is going to be equal to the change in the concentration of I2 over a change in time. So one aspect of what we'll have to do is have a stopwatch and time things. And so what you'll see on the videos is there'll be an iPad with a timer on it, and I'll hit it and you have to watch the video, okay? Or watch the time and try to record when you see the color change, okay? So, and I'll explain to you why I'm talking about the color change here in just a second. So now, how do you make a consistent measurement of the iodine concentration? And it turns out they have this really clever mechanism for this type of reaction where iodine is involved, and that is to react it with thiosulfate. Okay, so if we take iodine and we react it with thiosulfate, S2O3 2 minus. So be careful. There's a lot of, and there's one more company. There's a lot of compounds here with sulfur in them. Right? What'll happen is the product of that reaction, one of the products is just I minus. It makes iodide. And there's another sort of byproduct. It's S2O6 2 minus. But we're not really looking at this. We're really just concerned about this main reaction on the top. So this is how we do the timing of the reaction. We always, for every trial that we run, this value is a fixed value, and you'll calculate it from its molarity and volume that you use when you add it to the solution. So there's a fixed amount of thiosulfate in the solution. So think about what's going to happen then. If it wasn't for the thiosulfate, the solution gradually turns brown. But it turns out this reaction going back to the iodide is very fast. This is a relatively slow reaction. So the consequence is, as long as there's some thiosulfate present in the solution, it will continually clear the iodide from the solution so you don't see it. Now, when the thiosulfate runs out, then the iodide can't be removed from the solution, and then you'll start to see a color change. Now, remember I told you this is a slow reaction, so the color change would be really slow. So what we do is we actually add an indicator, which is just starch. And in the presence of a small amount of iodine, what happens with starch is it turns that dark bluish color. I don't know if when you were a kid, you made color prints from potatoes, but that color was actually a complex that's formed between iodine and the starch in the potato, okay, the carbohydrate. So um, that's how we're going to do the timing. So think about it like this then. We have a fixed amount in every reaction of moles, right? And remember, we want to know the change in moles per liter, right, the molarity, per unit time. So we'll have a volume for the solution. We'll have a fixed amount of thiosulfate that reacts. So this is a 1-to-1, this is a 2-to-1 stoichiometry, okay? So we can use stoichiometry to figure out how much I2 was created in the reaction. And then what we can do from that is divide by the volume to get the molarity. And then we can divide by the time that we measured to get the rate, right? So relatively straightforward experiment to do. The hardest part is to get the accurate timings on your reaction. Fortunately, when you do this on a video, you can pause the video and go back and try to see when you saw the color transition first occur. And it's the first presence of color. It's not when the whole thing goes dark, but it's that first presence of color that we're like trying to look for. So it's a relatively easy thing to see, and because you can stop the video, you can get the time. Okay, so that's sort of the overview of the reaction. Iodide plus persulfate will produce iodine, right? And it's the moles of thiosulfate that we add that tells us how much iodine has reacted when it changes color. Okay, so we'll get a color change. It turns dark blue, and then we can use that information to calculate the change in concentration of iodine, and then we can use that to calculate the rate of the reaction. So, having said that, that's how the mechanics of the reaction work. The way the experiment works then is we're going to change these values. So I'll take the I minus, the iodide concentration, and I'll say double it. In fact, I think we actually half the concentration. Well, if there's a dependence on the reaction on the iodide concentration, we'll see it as a change in the rate. Now, if it's a 1-to-1, it's first order. If it's like a 1-to-1 correspondence in the change, then it's first order. So if I double the iodide, I should double the rate, for example. But if it's second order, right, if I double or half the iodide, it'll be either quadruple or become 1/4. And then if it's 0 order, then what happens is there's no change. So you'll change the concentration and you won't see a change in the rate. In terms of concept, how that works in the experiment, it has to do with the amount of time that it takes for the reaction to change color. So for a 0 order reaction, it changes color at the same time every time. Doesn't matter what the concentration is. If it's a second order reaction, right, and you have the concentration, then it should take twice as much time because the time is in the denominator. So these are things to think about while you do your calculations. We'll look at 2 other aspects really of this reaction. We'll try to get at the activation of the energy of the reaction by measuring the rate of the reaction, or the rate constant of the reaction, as it changes as we change the temperature. Okay, so we're going to have a couple of different temperatures. We'll have a couple of different rate constants. We'll be able to create an Arrhenius plot, and from the Arrhenius plot, we should be able to get the rate con? So we should be able to get the activation energy for the reaction, is what I meant to say. So that's one aspect. We're going to do the kinetic studies to figure out what the activation energy is. And then the third one, it is really hard to do. But if you add a catalyst, what does it do, right? It makes the reaction faster. So we're going to try doing this reaction in the presence of a catalyst. And at this point, I can't even tell you, like when you do these experiments, you don't really know how efficient the catalyst is going to be unless you do lots and lots of experiments. So you'll have to watch the video and try to figure out, like, did the catalyst make a difference? Was I able to measure the increase in the rate caused by the catalyst? Those are the kind of questions we'll be answering at the end of this lab in the write-up.
Okay, so this is the first part of the experiment. We're going to be setting up for the reaction, and you'll notice in this experiment 1, we're going to use 5 mils of Ki. Now, this is going to be like a dilution equation. There's 5 mils and a total of, and then you just have to add all this up. I think for the most part, you can ignore the volume of the 2 drops, since there's only there's 20 drops to a milliliter roughly. So we'll ignore that. But there's 5 plus 2.5 plus 5, so that's 12.5 milliliters. That's what you'll have to take as your total volume. And then the dilution, you'll be adding 5 of this, but for this you'll be adding 2.5, okay? So what you need to do, or what we're going to do in this video experiment is go ahead and set up these volumes. Now I'll show you what I did, and I always try to emphasize this in my videos because I'm working alone and you have to be super organized. But this is kind of true in any sort of research endeavor as well. I set it all up. This is actually the table in front of you. Each one of those pipettes represents one of these solutions. You'll notice I have the test tube here. These are my solutions. Each one has its own pipette. Now the pipettes are set to 2.5 milliliters because as I looked at this table, I noticed that everything was in increments of 2.5. And so if I set them to 2.5, I don't have to reset them to 5. I'll just do those twice, okay? This is the next set of solutions. I'll have to back up because there's a lot of them, right? And this one just takes a dropper. This is the starch indicator, but this is your sulfate solution, etc., your persulfate, and etc., that kind of stuff. So that's your other, not persulfate, no, I almost said thiosulfate solution. Other thing I wanted you to notice is, remember, the thiosulfate is what we'll be using for the timing of the reaction. That's the only one where the volume is constant throughout. So it's the same number of moles of thiosulfate in every experiment. Okay, so what I'm going to do is go ahead and take 5 mils of this and 0 of this. So basically it'll be 5 mils of Ki in here. And then I'll do 0 mils of this. I'll do 2.5 mils of this, 2 drops of this, and 5 mils of this according to this table. Then what I'm going to do is I'll take, and that will be in this larger test tube. Then what I'll do is take the contents of the smaller test tube, place it in the contents of the larger test tube. I'll mix it on my vortex mixer. I don't know if you can see that vibrating, but it's a vortex mixer, for 1 second or maybe 2 seconds. We'll see how long it takes to mix. And then I'm going to have it mounted into this rack. There will be a timer right next to it so you can see the time. And I'll start that timer, or try to start that timer, as soon as I mix the 2 solutions. Okay, so the next thing that you'll see is the 2 solutions right before I mix them, the starting of the timer, the vortexing, and then we'll watch to see the reaction change color. So what I'm going to do is slightly different than what I said I was going to do. I'm going to go ahead and mix these together. This is the small tube and the large tube. And then I'm going to set it in here. I'm just going to vortex them together, and we'll try to watch it in the test tube while it's vortexing and see if that gives us a nice, consistent, and quick color change, okay? So this is what I'm going to do. I'm going to add this together, start this, vortex this. And we'll just watch this to see how long it takes. It's 24 seconds roughly. Well, you'll have to go back and pause when you see that color change, okay? So this is trial 2 for experiment 1, and if the times are close enough, we'll go ahead and stop there and go on to the next experiment. So again, I'll add these together, start the timer, and mix. Go back and record the time when you saw the color start to change. Okay. So as we do experiment 2, keep in mind that we have not changed the amount of Ki. I have not added any KCl, so this volume is 5 milliliters. But what we've done here is added 2.5 mils of K2SO4. Now the K2SO4 doesn't actually do anything in the reaction, but it makes up for the volume of persulfate that we're not adding. You'll notice it went from 5 to 2.5. So now if you take this total volume on this side, it's 7.5 mils, ignoring the drop, just as it was in trial 1. So we're trying to keep the total volume the same, but adding this to substitute for this. Now this doesn't do anything, so this concentration in the final solution is essentially 1/2 of its original concentration. So I set these up so they're a little closer to each other in terms of focal plane, so you can see both a little more clearly. So I'll add this and we'll start the timer and mix. This is, by the way, trial 1 of experiment 2. Right, you can see color. Yeah, so go back to when the color first appeared and then record that time for the trial 1 of experiment 2. For trial 2 of experiment 2, mix that up a little bit before we put them together. So when I looked at the videos for trials 1 and 2 of experiment 2, they didn't look that close to me. I didn't look exactly. So what I'm going to do is do a third trial, and then you'll use the 2 that are closest together. I only need to mix this up a little bit before, and then I'm going to add these 2 together, start the timer, and mix. There you go. All right. So go ahead and look at the first change of color. You have 3 trials to look at. Take the 2 that are closest together in terms of time, and those will be the trials you use for your calculations. So this is experiment 3, trial 1. This is experiment 3, trial 2. Okay, stop the video and look back and record that time. This is experiment 3, trial 3. I forgot to mention, there are 3 trials for trial 3, just like there were. Okay, so the next part of the experiment, what we'll be doing is repeating experiment 1, but recording the temperature again. And I've been monitoring it, it's been sticking close to 25, but this time we'll record it as well as run the reaction. And then what we'll be doing is running the reaction at a series of different temperatures. And this will allow us to determine what the threshold, what the activation energy is that the molecules need to overcome for a reaction to take place. So when 2 molecules come together, right, we talk about collision theory in class, they have to have proper orientation, and they have to have a collision, right? And the collision also has to have sufficient energy. That energy predominantly is for breaking bonds and making new bonds. And so what we'll be doing by changing the temperatures, changing the energy, and the way in which the reaction rate changes as temperature changes will tell us something about that activation energy. You'll generate what's called an Arrhenius plot, and that's the generally accepted way for determining what the activation energy is. So this will be the room temperature run, and right after the experiment we'll measure the temperature, but it's been around 24.6 to 24.8 degrees. We'll see how close we are. Okay, so we'll go ahead and do this. I need to mix this one up before I mix together. I'll go ahead and do this, and then hit start, go like that. Now, if you remember when we did this, I believe it was between about 25 and 30 seconds, so that's kind of what we're shooting for. Hopefully things haven't changed. There we go. Now you'll have to go back and pause and record what that time was. But what we'll do now is we'll focus on where the temperature comes to. And it looks like it's, like I said, around 24.7 degrees, okay? So take that as your temperature for room temperature. The other temperatures we're going to do will predominantly be cooler, and we're only going to do 3 or 4 for our Arrhenius plot, okay? Okay, so this is going to be the next trial for the temperature trials, and you'll notice I have those two stuck in test tubes. Currently, the large test tube is measuring at 1.6 degrees. That actually took about 3 or 4 minutes to get to sort of a stable temperature. So what we're going to go ahead and do is do what we normally do. We'll mix the two together and record the time it takes for the color to change. At the end, just like we did in our previous trial, we'll go ahead and record the temperature in the larger tube. It may be a little harder to see, so we have to look very closely. It's cold enough that it's frosting over a little or clouding over on the outside. Looks like that did it. So we'll drop the thermometer. You'll have to go back and see at what time that took place. We'll drop the thermometer in and see where that ends up at. So it's actually warmed up considerably. We're right around 7.4, 7.5 degrees Celsius at the lowest, okay? So this will be our second temperature data point. Again, I cooled these down and then I warmed them up a little just by placing in my hands. Try to get the temperature up about 10 degrees. I'll mix these together, start the time, and we'll record the time that it takes to change color. Go. And then stopped it, forgot I was going to record the temperature. Let's see what our temperature is. So right around 16.7. I had my fingers on the glass down there below, so I probably warmed it up a little bit. I try to move them up. but it was around 16.7, the lowest, okay? So for the next experiment, we're doing an elevated temperature. I just took some hot water and sat the test tubes in there for a little bit, for about 2 minutes, until I got about to where I wanted to be in temperature. Oh, and we'll start that up. That was bad. Oh, darn it. See how quickly that changed. We should probably redo that. That'll make a significant impact. So we'll go ahead and stop this one. I'll record the temperature so you can see about what it was. And perhaps this is going to be accurate, but it was supposed to be, yeah, right around 30 degrees. This one's going to be at, looks like around 31 point, see if you can bring that a little closer, 31.4 degrees Celsius. So we'll redo that, and hopefully we'll get similar results, but we didn't start the time quick enough. Okay, so we're going to try a second trial of this elevated temperature. This was, again, about the same temperature. Really, the way I'm doing this is I got a hot water bath, and I'm allowing it to cool down, and then I control the time that the test tubes are in to keep their temperature below about 35 degrees. This is the thermometer. I just stick it in there and I monitor the temperature. The reason I do that is because thiosulfate breaks down at higher temperatures, and so the longer it sits in there, the more of a false value that it'll give you for your final result. So let me mix this up real quick, and I'm going to add this and we'll start the time. So you'll record the first appearance of the color, not when everything changes, but as soon as you see the color change. And that was pretty early on there, actually. So for this last part, we're going to try to look at the effect of a catalyst. And when we look at the table, and I'll change this in the copy that you see, everything's going to be the same here. We're going to do experiment 1. We'll do it at room temperature at first. And then what we'll do is we'll go ahead and not add 0.25 mils, but 0.10 mLs of this copper sulfate solution. Now, think about how that affects the overall concentration, because we're not compensating for it in any way by taking volume out of the others. But this is going to be 0.1 mils out of about 12.5 mils. So it's less than a 1% change in the concentrations, because the volume of this amount, this is going to, again, be 0.1 mils, is so much lower than the rest of the other volumes, it won't have a large effect on their concentrations. So we're going to do the first one at room temperature, and then we'll do 0 degrees Celsius, and then we'll try to do one temperature in between. So we're ready to do our room temperature trial with catalyst. I'll mix the two together, hit the start as soon as I do that, and start mixing at the same time. I don't know if you saw that. That's kind of what I expected would happen. Catalyst makes the reaction so fast, at least at room temperature, you can't tell that there's any delay between the reaction and when you mix the two solutions together. So go back and see if you can see a time, but I'm pretty sure you won't be able to have an accurate time. It'll be basically be as soon as I poured them together. So anyways, but take that as sort of like an indicator of how effective a catalyst can be when it lowers the activation energy. Okay, so we're ready to do a low temperature trial. I'll mix them together and start the timer. Go, and then we'll measure the temperature. And you'll have to stop the video and go back and see what that time was. And we'll take the lowest temperature that we see on this thermometer. is about 6.6, I believe. You'll have to go again. Like on the video, you can go back and look to see what the lowest temperature was. Okay, we're ready for the next low temperature trial. This should be slightly higher temperature. I'm not sure I can get lower than the temperature I just got in the previous segment, but this one is easier to always get higher temperatures. So this should be between that temperature and room temperature. So I'll mix, start the timer, start mixing. Again, this is a somewhat higher temperature. Oh, it already went. Well, you might be able to measure that. It's just a few seconds, I believe. You'll have to go back in the video and see what that was. Stick the thermometer in here, and we'll see what the temperature is. Get my fingers off of there. Oh, sorry. So 14.2, 14.1. It looks like 14.1 degrees Celsius is our lowest temperature. I'll do one more and I'll try to get a temperature that's lower than the first one. I think I might be able to do it, but I'm going to have to take a little finagling, so hopefully we can do that. Okay, so we're ready to do our lowest temperature, hopefully. And so I'll go ahead and mix these two together. Start it. Okay, there we go. We have a color change, and we'll throw the thermometer in real quick and be able to get a fairly accurate temperature, I think, from this one. Again, lowest observed temperature. So it looks like about 1.7 degrees Celsius is what it dropped to. And to think about what's going on, it's heating up in the air, plus the thermometer has to cool down, so they're going to meet somewhere. So really the lowest temperature is probably a little bit lower than that. But yeah, 1.7 seems like a fairly reasonable number. All right, so go back in the video. You can get your time for that temperature. And should be able to construct a reasonable Arrhenius plot from the temperature data that we were able to obtain with a catalyst.